Beneath forest floors, lignin binds fallen wood into stubborn brown architecture, season after season. It is one of Earth's great stores of aromatic carbon packed into plant walls. Rain can soften it, but water alone cannot open it, no matter how long it lingers. Inside each branch, tough bonds guard color, strength, and time through weather and insects. This locked material shaped forests long before people understood chemistry or named its architecture. It also shaped one of humanity's most patient surface arts, preserved in lacquer. In East Asia, a wounded lacquer tree offered a pale, sticky sap. Left in moist air, the sap darkened into a smooth, hard, protective skin. The change seemed like magic, borrowed from breath, darkness, and patient hands. Yet nature had already written the recipe inside living tissues, long before books. White rot fungi entered fallen trunks as quiet chemists of the woodland, beneath moss. Their threads explored cell walls, searching the locked brown scaffold within the wood. They released copper enzymes that touched phenolic rings with oxygen and air. Among them, laccase became one of biology's most elegant, quiet oxidizers. It did not break wood with flame, pressure, or industrial violence. It invited electrons to move and bonds to reconsider their loyalties inside matter. Long before laboratories named it, artisans watched lacquer cure in humid rooms, generation after generation. Japanese urushi bowls hardened through days of shadow and steady moisture in wooden cabinets. The sap carried a shimmering mixture called urushiol from the lacquer tree. Air met that sap, and a liquid became a lasting film beneath artisans' fingers. In the 1880s, a young Japanese chemist studied this transformation with unusual care. Hikorokuro Yoshida examined lacquer sap within Tokyo's new chemical laboratories among glass bottles. He saw the sap consume oxygen while its color deepened, without burning. In 1883, Yoshida described an oxidizing substance inside the latex and linked it to hardening. His paper gave science its first clear glimpse of laccase in a craft material. The name came from lacquer, the craft that had revealed it and gave it a lasting name. A handmade surface had led directly to an invisible catalyst beneath a glossy bowl. Yoshida connected human art, tree defense, and oxygen chemistry in one observation. Soon, European chemists pursued similar oxidizers in plants and fungi under microscopes and flasks. In 1896, Bertrand and Laborde reported a related oxidase from fungi. By the late 19th century, laccase was no longer a curiosity on laboratory benches. It had become a doorway into pigments, browning, and living surfaces all around organisms. Fungal laccases then widened the story beyond lacquer trees and into forests. Researchers found them in mushrooms, molds, and decaying woodland litter where damp wood softened. The forest, not the factory, had been the first workshop all along. On rotting logs, laccase helped turn hardness back toward soil after rain. A laccase molecule is small, folded, and built around copper rather than iron. The copper atoms sit like hidden beads inside the protein, out of sight. One copper center receives electrons from a colored or phenolic molecule at the surface. Deeper copper centers pass those electrons to oxygen inside the folded enzyme. The oxygen is reduced to water, leaving no harsh residue as the final gift. The touched molecule becomes reactive, ready to link, fade, or open in its neighborhood. This is laccase's quiet power, persuasion through tiny electron movements, not destruction. Sometimes helper molecules carry its influence into larger, stubborn structures when direct touch is impossible. Together they can loosen stains, modify fibers, or reshape lignin in watery surroundings. In wood, laccase joins the slow choreography of decay beneath moss and beetles. It helps return fallen trunks to soil, minerals, and new growth. In mushrooms, it shapes pigments and protects delicate fruiting bodies. In plants, laccase-like enzymes help build strong cell walls. The same chemistry found new roles as industry sought gentler tools. Papermakers studied laccase for cleaner ways to manage pulp color. Textile processors explored it to soften dyeing and finishing steps. In denim, it could help fade indigo with less chemical burden. In cork and wood products, it offered new routes for bonding. In wine and juice, laccase from damaged grapes became carefully monitored. In bakeries and food science, it can influence texture and color. In biorefineries, laccase offers paths to transform plant residues. Wastewater researchers value its appetite for many persistent colored molecules. It can help turn troubling dyes into less visible chemistry. Scientists also study laccase in sensors for environmental and food signals. Its promise lies not in brute force, but in selectivity. The enzyme works in water, often using air as its partner. That simple partnership made laccase a symbol of greener processing. Still, every use depends on context, material, and careful design. The old lacquer bowl reminds us where the story began. A wound in a tree became a window into catalysis. A darkening sap taught chemists that air could be guided. A forest fungus showed industry how decomposition can become renewal. Today, laccase stands between craft, ecology, and sustainable chemistry. Its future may be written in quieter mills, cleaner waters, and living carbon. Enzymes Bio began with a simple frustration we kept hearing. Sourcing many enzymes meant many suppliers and slow paperwork. We made it one place. Cleaner chemistry, ready for the future. Discover it at enzymes.bio.